Hello, everyone, and welcome to the presentation of our paper, simTPM, a user-centric TPM for mobile devices. As Inzia already introduced, my name is Dhiman, and this work is jointly done with Luchan Hanslik and Sven Bugil. TPM, or a Trusted Platform Module, is a de facto industry standard for trusted computing. Solutions like BitLocker, Intel TXT, or Chrome OS actively uses various TPM features like secure storage, crypto coprocessing, measured boot, or extended authorization policies. In a desktop domain, TPM being the trusted computing agent, it tries to serve with all of its features to most of the stakeholders that is active in the domain. But when we see in the mobile domain, the only available implementation of a TPM is a Microsoft FTPM, which is solely designed for Microsoft devices, catered only for the system applications and operating system. This creates a gap for the other stakeholders, those are active in the domain. This motivates us to create a user-centric TPM for mobile devices, and we choose the SIM card as the representation of the users. Before going deep into the design and implementation of the SIM card, we wanted to see that where in the landscape of trusted computing, our implementation is the best fit. For that one, we devised a systematization of existing TPM technologies, comparing technologies like Microsoft FTPM, Intel SGX, and two variants of IBM's virtual TPM from the server domain, one supported by a hardware TPM, and another one is supported by a secure coprocessor. Though here, the Intel SGX is not a TPM technology, but many of its features are similar to a hardware TPM, and in recent research past, we can see that there are a handful of tries to implement software TPMs inside the enclave of the Intel SGX to provide trusted computing to the users. Now, to do a systematization, we need a set of objectives. Here, the objective S1 to S6 and A1 to A3 are our interpretation of trusted computing groups provided specification for hardware TPM and mobile trusted module specifications. The objective D1 and D2 are the objectives that we think a SIM-based TPM should have. And the objective D3, that is bound RTM or bound root of trust of measurements, I'm going to present later in the slides. To create a baseline for our systematization, we use the hardware TPM with our objectives, and we immediately find out that except the mobile availability and movability, a hardware TPM supports all of the objectives. And this is no surprise because the hardware TPM was never designed for mobile devices. Due to time constraint, I am unable to talk about how we devise all the objectives, but I will talk about a handful of them. In my motivational slides, I already talked about multiple stakeholder and the current scenario in the mobile domain with the multiple stakeholder objective. The other two objectives that I want to talk about are early availability and bound RTM. Early availability is important for measured boot. In a multi-module boot chain, with a measured boot, each and every component tries to measure the next component that will going to be in the chain, store the measurement inside the TPM, and then transfer the control to the next component. To have this measured boot from the beginning of the boot chain, a TPM has to be early available. In our systematization, we find out that both SGX and FTPM does not support this objective. For SGX, this is no surprise again because SGX was never designed to support this objective. But interestingly, FTPM also does not support this objective due to the fact that FTPM is being a trusted application running inside the trusted execution environment, or in the figure you can see that's called TEE, which appears late in the boot chain. The next objective I want to talk about is bound RTM or bound root of trust of measurement. This is important for a trustworthy measured boot because the first measurement that is coming in a measured boot chain should come from a trustworthy component. Otherwise, any arbitrary component in the boot chain suddenly can send fake measurement to the TPM and end up having an untrustworthy measured boot chain. So we define bound RTM as the first measurement reported to TPM has to come from RTM for a trustworthy chain of trust. Now, this property in today's implementation is kind of a God-given property just because TPM and RTM both are part of the silicon. and TCG provides no guideline to define how this objective can be achieved in real-life devices. In our systematization, interestingly, we found out that both of the VTPM implementation does not support, and also VTPM with secure coprocessor in retrospective does not support completely this objective. This is due to the fact that the secure coprocessor is connected using a PCIe bus to the device, and there is no guarantee that the first measurement that is coming to the secure coprocessor is coming from a trustworthy RTM. The rest of the systematization is available on the paper, and again, due to time constraint, I couldn't able to present all of the comparisons. But the knowledge that we gathered from this systematization, we then started designing our TPM inside the SIM card. Now, SIM cards are general purpose smart cards. It has its own operating system. For example, could be Java Card OS or Multos OS. It has its own processor. It has its own memory inside the card. So these are small computers in our pockets. SIM card supports multiple applets, and the security manager applet that resides within the SIM cards assures the applet segregation. So we leveraged this capability of the SIM card, and we implemented the simTPM as a separate applet inside the SIM card. We introduced a secure non-volatile storage and a PCR bank for the TPM applet just by using some of the non-volatile storage offered by the smart card. The communication with this kind of smart card or SIM card normally happens with application protocol data unit commands or APDU commands, which are ISO standards. So we devised some custom APDU commands using those, the components, those are outside environment of the SIM card can communicate to our simTPM applet. As I already mentioned that these SIM cards are having their own coprocessor, so we can use this coprocessor for cryptography that is working completely isolated from the rest of the device. But the limitation the SIM cards are having is that the SIM card does not support modular multiplication or ecliptic curve point addition. Due to the fact we cannot introduce a general TPM remote attestation in these SIM cards. So to overcome this problem, we introduced a new crypto building block for remote attestation, which will execute this remote attestation solely within the TPM without host involvement. All crypto primitives and proofs are available in the paper, and again, due to time constraint, I'm kind of unable to present the proofs here. But one point I want to make clear here, that this crypto that we implemented are the building block for the whole TPM applet that is working inside the SIM card, and if someone doesn't like our crypto implementation, just implement your own cryptography within the card and just run the simTPM as you want. And to our knowledge, Orange Lab does have similar implementation, but unfortunately, that implementation is not available to the public. Next, for a TPM, we need trustworthy endorsement. To introduce trustworthy endorsement in simTPM, we followed the same approach of a hardware TPM that we implemented unique asymmetric endorsement key inside our TPM applet. This endorsement key will stay active as long as the TPM applet will be alive. This will help us to differentiate between a genuine and a rogue TPM. Another important point for a TPM is that TPM needs a trusted clock. In a mobile device, SIM card generally draws its clock from the baseband processor, and by design, the baseband processor is completely segregated from the rest of the software stack that is running on the mobile device. So this baseband processor, due to its design, can be a secure clock source for the simTPM as well. So till now, I talked about how we designed and implemented the TPM inside the SIM card. The next question comes is that how we are integrating this simTPM with a mobile device. For that one, we use Android as a target operating system just because it is open source. We used ARM Trusted Firmware, again, because it's an open source bootloader that runs with Android. And we use HiKey 960 board as a hardware platform. So we added SIM card communication to each and every submodule of the bootloader. This will help us to achieve the objective of early availability. And then we introduced new radio interface library that houses the custom APDU commands that we already devised to communicate to the simTPM, so that the Android operating system, or even the third-party applications, or through the third-party applications, the user can communicate to the simTPM for their trusted computing need. This helps us to achieve the objective of multiple stakeholder. At this point, we again stumble to the same problem, that how we are binding our simTPM with the RTM, because our simTPM is having a user-centric nature, and due to that fact, the simTPM is movable. So to overcome this problem, we propose two solutions. One is using the trusted execution environment, or TEE, as a TPM proxy, and the another one is using a kind of distance bounding protocol. In trusted execution environment and as a TPM proxy, what we did, that we created a secure end-to-end channel using the device-specific key that is solely available to the trusted execution environment. And the simTPM only reacts to the command that is coming through this channel. So this will make sure that the simTPM is actually talking to a securely, trustedly booted up trusted execution environment that is running inside an untampered device. And simTPM will release data only through this channel. Now, this proposal is having some shortcomings, that this limits the early availability of the simTPM, because the simTPM has to wait till the trusted execution environment is available late in the boot chain. Otherwise, the secure end-to-end channel will not going to start. But this can be overcome by designing the bootloader such a way that they will pass the measurement through the trusted execution environment. And the Microsoft FTPM could have been extended this way to achieve measured boot. The other way that we try to bind our RTM with the simTPM is by using a distance bounding protocol, where the simTPM and the RTM will run a timed protocol using the first measurement that is coming from the RTM to the SIM card. That will make the simTPM to understand that it is actually talking to the RTM that is residing on the device where the simTPM is also connected. We ran some experiment for our distance bounding protocol, and we end up having a 721 microsecond threshold with 83% success rate of successful boot. In a practical situation, for a practical attacker with a 50 Mbits relay network, his chance will be 0.1% to break this protocol. But at the end, this is a probabilistic game. So a more powerful attacker can increase the probability of defeating the game. So we designed the TPM. We integrated the TPM with the device. At this point, we again went back to our systematization objectives to find out, are we matching with our systematization objectives or not? And there we find out that except the bound RTM, all of the other objectives are met with simTPM. This is due to the fact that we wanted to make our simTPM a user-centric TPM. That means that the simTPM is currently active on device 1, and user will move the simTPM to device 2, and suddenly the user-centric secure storage will be available on the device 2. Due to that, we need to make a trade-off with the bound RTM point. Now, the bigger question comes that, is this implementation is a practical implementation or not? For that one, we devised two different implementations of Infineon TPM 2.0. One is running in a Lenovo laptop. We call it as an emp-TPM or embedded TPM. And another one is a plug-and-play TPM that is running on a Raspberry Pi. We call it Pi TPM. Our simTPM is running on a Hikey 960 board, where the software stack is run by Android. So we selected some of the frequently used TPM commands, and then we ran the commands 50 times to get our numbers to create the performance analysis. The first set of commands that we used are the cryptographic commands. Those are ECC keygen, that is on the top left, hash on the top right, TPM seal on the bottom left, and TPM unseal on the bottom right. And here we can see that emp-TPM or embedded TPM is a clear winner. You can see that in the picture, embedded TPM is in the middle row. But the simTPM, that is on the left row, the numbers are on par with the plug-and-play TPM, that is the Pi TPM, running on a Raspberry Pi on the right row of the picture. Exactly why we have these particular graphs is a little bit hard for us to answer because we cannot completely answer this question due to the fact that the implementation of the Infineon TPM is not publicly available. The next set of commands that we tried here are the TPM-specific commands. The top left is, again, the PCR read, top right is PCR extend, and bottom left is random number generator. Here, we can see that the simTPM is a clear winner, except the PCR extend commands. This happens because our PCR extend implementation is a software-only implementation, and which is also unoptimized implementation. So with the support of more support from the hardware platform, this PCR extend implementation could have been optimized in a better way so that the results could have been better. So from the performance evaluation, we can conclude that there is no clear winner. And our implementation of this simTPM prototype can be a practical implementation. Before I conclude my talk, I want to talk about NIST challenge that is currently going on where they wanted to use the SIM card as a security element for mobile devices. And as we, in future, going to add the FIDO protocol on top of our simTPM, we think that our implementation could have been a really good fit for this challenge. And we can go for this $100,000, which is not a less money to win. But unfortunately, our team consists of a German, a Pole, and an Indian, and we don't have any US passport holder. And because of that, we cannot join this challenge. But OK, the deadlines are over, so we cannot go for this challenge anymore. But in future, we would love to collaborate with anyone who comes with a US passport. So, so in conclusion, in this project, we probably the first time we did a systematization of existing trusted platform module technologies to see what is the current situation. Then we find out the gaps in mobile domain through our systematization. To fill the gap, we designed a TPM that runs in the simTPM, having both user-centric and device-centric nature. Then we tried to provide two ways to bind this TPM with the RTM. And through our performance evaluation, we try to show that our implementation is a practical implementation. And on that note, I would like to thank you guys for listening to me.
Thanks, speaker. Any questions?
Hi, I'm Mohammed. So my basic question is going to be like, for example, in my iPhone, I can take out the SIM card. And if I have access to any of the Android device, and I don't know the password, but if I can take out the SIM card, and I reverse engineer and all the stuff, and then I'll be able to steal the passwords and all the stuff?
Yes. Our implementation is having two aspects. One is the device-centric aspect, another one is the user-centric aspect. The device-centric part keeps the measurement that comes from the device, and the user-centric parts will keep the password that is the user is using. So if you take the SIM card out of your iPhone and put it in an Android device, there will be an authorization policy running so that it will identify that it is talking to the correct user or not. If that part is complete, then the user-centric part where your keys are available will be available, but the device-centric part will never be available because the UUID of the device will never going to match with the stored inside the TPM.
So in TPM, you only release the secrets once you authenticate the running device or running host?
Yeah.
OK. Thank you.
Okay. So thanks for the talk. So did I hear correctly? Does the security of the scheme depend on the assumption that the baseband subsystem is trusted?
I cannot get you. Can you be a bit?
Does the security of the scheme depend on the assumption that the baseband subsystem is trusted?
Yes.
So
generally, the baseband processor, the software that is running inside is like once installed, never going to change. So, and the rest of the software system cannot actually go and suddenly change the clock that is running for the baseband processor. So this is an assumption that we use, that the baseband processor is a secure processor.
So I guess I should have introduced myself. I'm Alex. I work at Qualcomm. But
Probably you broke some baseband
Just late.
processor previously.
but I guess so. If you already trust the baseband, why not just implement everything on the baseband processor? It has a lot more power and a lot less.
Oh yeah, definitely,
constraints
definitely. Then the problem will happen that again your TPM will become a device-bound TPM, and the user-centric nature that we want to introduce here will completely go away. So that will give you a device TPM running on a chip. So yeah, simply you can do that one.
Okay,
but
right.
then if you ask, okay, give me a key from the TPM, it will give you, but your device will be bricked, and you don't have that key anymore. Where still you can recover the key in the simTPM infrastructure.
Thank you.
Hi, I'm Sarah at Square. It sounds like your implementation is actually can be generalized to just smart cards in general and not just SIM cards. Is that correct?
We didn't implement in general SIM card because the general SIM cards are normally encrypted with the key that is provided by the telcos. So we did it on a programmable SIM card, but if we get support from the telcos, it can be implemented in a general SIM card.
I meant more like generalized smart cards. So like anything that implements the smart
Yeah,
card.
yeah, yeah. Any SIM card that you can cut into the form of a SIM card and then can go and talk to your phone through the SIM slot that is available on your phone, this library will work in that one.
Oh, because the crazy idea I have is like imagine if you take, so the EMV protocol happens on various smart cards. Have you considered doing something ridiculous by seeing if a TPM could run on someone's credit card?
I cannot get the last part of the question.
Oh, okay. So EMV is the Europay MasterCard Visa protocol. It's the standard in which chip and pin happens for, and it's using the smart card kind of form factor. So the ridiculous idea is, what if you ran a TPM on someone's credit card?
Yeah, you can. It's just, for our implementation, we need 64 kilobytes of space to implement the whole TPM. So if the card can provide that much of space, you can.
Yeah, thank you.
Okay, let's next speaker again.